Hello guys, welcome to our Calculus Diwali project, which is assigned by Professor Manish Gupta and Sudeep Behra. So, our project topic is optimization of trajectories for interplanetary space travel, which is a quite unique one. Let's explore the project in depth. Let's take a brief introduction to our topic. In this 21st century, optimization is one of the most useful needs of the human due to lacking availability of the resources. Sending spacecraft to a planet requires the use of lot of the resources. So to reduce the resources, we come up with the optimization idea as a problem in our project. Now let's start our project journey. There are many challenges faced while sending a spacecraft to space. Some of them are vast distances, gravitational forces, limited fuel resources, navigating gravity wells, interplanetary environmental factors, and advanced exploration objectives. Now we see some of the importance of optimization. Optimization is very necessary in this current century. In our project, it increases cost effectiveness, fuel efficiency, extended mission duration, exploration capability, and adaptability to changing conditions. Method used in our optimization approach are listed below. These are Hohmann transfer, solution to less fuel and energy, gravity assist also known as gravity slingshot, Oberth effect, multi-stage rocket system, aero capture, and last stage solar cells. Here we comes to our first topic, which is Hohmann transfer method. The Hohmann transfer orbit is a fuel efficient way to transfer a spacecraft between two circular orbits in space. The main aim of this method is to reduce the fuel usage. It involves two engine burns. The first to move the spacecraft from its initial orbit into an elliptical transfer orbit, and the second to adjust the spacecraft speed and transition into desired circular orbit at the destination. This image helps us to find the change in velocity and the velocity of the rocket in the orbit. The velocity of the rocket at the circular orbit are denoted by Vc1 and Vc2. Hence, the change in velocity, that is impulse, required to produce at perigee and apogee are delta V pi and delta V alpha, which are listed below. But there is one condition which is important to note in this method. If the initial orbit has a radius larger than the final orbit, then same strategy can be followed, but in this time negative impulse is produced. As a result, the rocket will decelerate, that is, its speed will be decreased. Now we reach to our next topic, which is cost of transfer in terms of mass. The cost of an orbit transfer in terms of mass of propellant needed depends on a few factors. Propellant use, thrust developed, rate of fuel consumption. These are the three major factors which contribute to the cost of transfer in terms of mass. The specific impulse is a performance parameter that quantifies the amount of thrust developed to the mass flow rate of propellant. It is given by ISP is equal to T by mg naught, where T is the thrust force. The mass flow rate is directly related to the time rate of change of vehicle mass. It is given as m equals to minus dm by dt. The force is given by mat is equal to T minus d minus mg sin gamma is equal to m dv by dt. If we consider space, then we can neglect the effect of drag force due to extremely rarefied atmosphere. As a result, the thrust produced can be considered to be constant. Then T is equal to m dv by dt, which is equal to minus isp dm by dt. Now we comes to our next topic, which is one of the most important in our project, which is solution to less fuel and energy. Launching a satellite from the equator helps the rocket to minimize its fuel usage. This is because at the equator, the rotational speed of the Earth is higher as compared to its poles. As a result, if we launch the rocket from the equator, it provides some extra momentum to it, which ultimately increases its speeds. Fuel efficiency. An optimal trajectory can also be increased if we send satellite from the equator. Polar orbit launches. Since the equator launches are optimal for reaching eastward orbit, polar orbit benefit from launching a satellite in the northward or southward direction. Now we come to our next method, which is gravity assist or gravity slingshot. The gravity slingshot, also known as gravity assist, is a spaceflight technique that uses the gravitational pull of a celestial body, such as a planet or a moon, to alter and boost the speed and trajectory of a spacecraft. By carefully planning the spacecraft's path and timing, it can gain or lose energy from the gravitational field of the celestial body, allowing it to increase its speed without expending additional fuel. This GIF helps you to understand and visualize gravity assist method in a better way. Calculating a gravity assist uses involves the uses of a vector algebra. It is given as v1 vector is equal to vp vector plus v infinity 1 vector, where v1 vector is entering heliocentric velocity of the spacecraft, vp vector is velocity vector of the planet, and v infinity 1 vector is entering hyperbolic axis velocity vector of the spacecraft. So the delta v vector from the gravity assist is simply the difference of v2 and v1 vector. That is, delta v vector is equal to v2 vector minus v1 vector, which is this GIF also describes the gravity assist. V infinity 1 vector. So, the total delta V from a gravity assist is simply the difference between the exciting hyperbolic axis velocity vector and the entering hyperbolic axis velocity vector. But if we fly closer to the planet, the gravity will bend our path more significantly, increasing our delta V. Here we comes to our next method, which is Oberth effect. Oberth effect is a principle in astronautics that states the efficiency of a rocket's propulsion system is maximized during power maneuvers at higher speed. According to Oberth effect, the energy gained during a rocket burn is directly proportional to the velocity of a rocket. Therefore, performing maneuvers such as the propulsion burn at higher speed results in more efficient and effective use of rocket energy, leading to greater overall effectiveness in changing the spacecraft trajectory. Oberth effect simply takes the advantage of the quadratic relationship between kinetic energy and velocity. The mechanical work done, W, is defined as the dot product of the force of the engine's thrust and the displacement it travels during the sum. Therefore, W is equal to Fs cos theta. If the burn is made in the prograde direction, then Fs cos theta is equal to F dot S. The work results in a change in kinetic energy as delta Ek is equal to F dot S. Differentiating with respect to time, we obtain dek by dt is equal to f dot ds by dt, which is basically dek by dt is equal to f dot v, where v is the velocity. Now, if we divide the above equation by mass, we get dek by dt is equal to fv by m, which is equal to a dot v, where a is the acceleration vector. Thus, we can say that the rate of gain of specific energy of every part of the rocket is proportional to speed, and given this, the equation can be integrated to calculate the overall increase in specific energy of the rocket. Here, the Oberth calculation for a parabolic unit is given below. It can be easily explained by the following equations. Our next optimization approach is multi-stage rocket system. A multi-stage rocket, a step rocket, is a launch vehicle that uses two or more rocket stages, each of which contains its own engine and propellant. A tandem or serial of stage is mounted on top of another stage. A parallel stage is attached alongside another stage. The result is effectively two or more rockets stacked on top of or attached next to each other. Two-stage rockets are quite common, but rockets with as many as 5 separate stages have been successfully launched. Now we see the performance of the multi-stage rocket. The reason multi-stage rockets are required is the limitation the law of physics places on the maximum velocity achievable by a rocket of a given fuel to dry mass ratio. This relation is basically given by classical rocket equation. At each stage, dry mass includes the propellant in the upper stage and each succeeding upper stage has reduced its dry mass by discarding the useless dry mass of the spent lower stages. This image describes how the multi-stage rocket system works. A further advantage is that each stage can use a different type of rocket engine, each tuned for its particular operating condition. Thus, the lower stage engines are designed for use at atmospheric pressure, while the upper stage can use engines suited to near vacuum conditions. This is one of the most important use of the multi-stage rocket. One of the most common measures of rocket efficiency is the specific impulse, which is defined as the thrust per flow rate of propellant consumption. It is given by ISP is equal to T by dm by dt into G naught. When rearranging the equation such that thrust is calculated as a result of other factors, we have T is equal to ISP into G naught into dm by dt. The common thrust to weight ratio of a vehicle is within the range of 1.3 to 2.0. For most non-final stages, thrust and specific impulse can be assumed constant, which allows the equation for burn time to be written as delta T is equal to ISP into G naught by T into m naught minus Fmap, where m naught and mf are initial and final masses of the spacecraft respectively. In order to calculate the burnout height and burnout velocity, this can be easily calculated by some calculation whose final equation is given as HB0 and VB0 are basically burnout height and burnout velocity respectively. Here we comes to our next topic, that is aero capture. Aero capture is an orbital transfer maneuver in which a spacecraft uses aerodynamic drag force from a single pass through a planetary atmosphere to decelerate and achieve an orbit insertion. Aerocapture uses a planet or moon's atmosphere to accomplish a quick, near propellantless orbit insertion maneuver to place a spacecraft in its science orbit. The aerodynamic drag force generated as the vehicle descends into the atmosphere slows the spacecraft without using its fuel. As a result, it is fuel efficient. The aerodynamic drag force F drag is given by the equation F drag is equal to half rho v square into ACD, where A is the reference area of the spacecraft. After the spacecraft slows enough to be captured by the planet, it exits the atmosphere and executes a small propulsive burn at the first apoapsis to raise the periapsis outside the atmosphere. Additional small burn may be required to correct apoapsis and inclination targeting errors before the initial science orbit is established. Atmospheric density ρ is a function of altitude and can be modeling using various atmospheric models. The equation for the atmospheric density ρ as a function of altitude h is given by the equation ρ of h is equal to ρ naught into e raised to minus h by capital H, where ρ of h is the atmospheric density at altitude h, ρ of 0 is the atmospheric density at sea level, and capital H is the scale height of the atmosphere, which represents the altitude at which the density decreases, e raised to minus 1 times sea level value. Here we comes to our last topic, which is solar cell. A solar cell is a spacecraft propulsion method that uses the pressure of sunlight to propel the spacecraft forward. It typically consists of a large thin reflective surface cell that captures and reflects photons from sunlight. As photons impact the cell, they transfer momentum to it, creating a continuous thrust. The solar cell method is very much fuel and energy efficient. As a result, it is also cost efficient. This image describes how the photons with energy strike to the cell, transferring momentum to the cell. The basic structure of solar cell is given below. The force F exerted by the sunlight on the solar cell can be expressed by the equation F is equal to 2p by c into A cos theta, where F is the force exerted by sunlight on the cell, p is the power of the incident sunlight, c is the speed of light, A is the effective area of the solar cell, and theta is the degree between solar cell and the direction of the sunlight. The factor 2 by c in the equation arises from the momentum of photon h by lambda and the speed of the light c, where h is Planck constant and lambda is the wavelength of light. This image describes how the photons incident and reflect from the cell, creating the direction of the thrust as shown. The total mechanical energy E of a spacecraft in orbit, including the energy gain from the solar cell, can be expressed by the equation E is equal to half mv square minus nu by r. This equation incorporates kinetic energy, gravitational potential energy, and the work done by the cell in changing the spacecraft's orbit. Several spacecraft have incorporated solar cell technology. With this, we conclude our project by giving various optimization approach which can help a space shuttle to minimize its fuel cost and energy. Thanks for watching out this video. Thank you.